Hello, dear students. Welcome back to another exciting step in our journey through triangles. Let me start with a simple observation. Have you ever looked at two photographs of the same monument, one big and one small, and wondered why they look exactly alike in shape? That's the beauty of similarity. Now, for triangles, the rule is quite clear. Two triangles are similar if two conditions hold true. First, their corresponding angles must be equal. Second, their corresponding sides must be in the same ratio. So if we write triangle ABC is similar to triangle DEF, then angle A equals angle D, angle B equals angle E, angle C equals angle F, and also A to B divided by D equals B to C divided by EF equals A to C divided by DF. When all angles are equal, we also call them equiangular triangles. These similarity conditions are the foundation for almost every geometric proof that follows. Hello students, let me take you back more than 2000 years to ancient Greece. Have you ever wondered how people back then, without calculators or advanced tools, studied geometry so deeply? One of the pioneers was Thales of Miletus, a mathematician who lived around 640 BC to 546 BC. Thales studied equiangular triangles, that is, triangles in which all corresponding angles are equal. His remarkable observation was this: the ratio of any two corresponding sides of equiangular triangles is always equal. Let's put that into math language. If we have triangle ABC and triangle DEF, and they are equiangular, then side A to be divided by side B to C equals side D divided by side EF. This means the side ratios remain constant, no matter how large or small the triangle is. This single observation later gave birth to one of the most powerful results in geometry, the Basic Proportionality Theorem, often abbreviated as BPT. It's not just an ancient idea, it forms the foundation of all modern similarity theorems that we study today. Think about this in real life. If you scale down a big triangle to make a smaller one, but keep the angles the same, the side ratios remain perfectly proportional. That's exactly why this principle is used in engineering, design, and even in mapmaking. So here's the quick insight. In equiangular triangles, side ratios are always preserved. That's the beauty of Thales' theorem. It connects angle equality directly to side proportionality. And that's why Thales is remembered as one of the fathers of geometry. In the next lesson, we'll see how this theorem leads directly into more advanced proportionality results, like the Basic Proportionality Theorem itself. Stay tuned. Hello students. Let's begin with a question. Have you ever seen how builders use ropes or beams to divide large triangular plots of land into smaller, proportional sections? Believe it or not, that idea goes all the way back to ancient geometry, and it's captured beautifully in the Basic Proportionality Theorem, also known as Thales' theorem. The statement of the theorem is simple but powerful. In a triangle, if a line is drawn parallel to one side, cutting across the other two sides, it divides those two sides in the same ratio. For example, in triangle ABC, suppose line D is drawn parallel to side B to C. Then the theorem tells us that side A to D divided by side D to B equals side A divided by side EC. Let's call this equation 1. What's amazing is that this proportionality holds true no matter how big or small the triangle is. Scale the triangle up or shrink it down, the ratios stay the same. That's the beauty of geometry. The relationship is size independent. This result is honored in the name of Thales of Miletus, the Greek mathematician who first observed these truths more than 2000 years ago. In fact, this theorem became one of the cornerstones for modern similarity theorems. So here's the quick insight. whenever a line is drawn parallel to one side of a triangle, it guarantees that the other two sides are divided in equal ratio. And that, students, is the foundation of the basic proportionality theorem. In the next lesson, we'll dive into its proof and see how this proportionality emerges step by step. Stay tuned. Hello, students. You've already seen the statement of the basic proportionality theorem. Now let's prove it together. This proof is not only simple, but also very elegant because it uses the concept of areas inside a triangle. Let's begin with construction. Take triangle ABC, draw a line D parallel to side B to C such that it cuts side A to B at D and side A to C at E. Next, from point D, draw a perpendicular DM to side A to C. Similarly, from point E, draw a perpendicular EN to side A to B. These perpendiculars will help us apply area formulas. Now let's compute the areas. The area of triangle BDE is given by 1/2 into base D to B into height DM. The area of triangle DEC is 1/2 into base EC into height DM. Notice that both areas use the same height DM. From this, we conclude that the ratio of area of triangle BDE to the area of triangle DEC equals side D to be divided by side EC. Let's call this equation 2. Similarly, if we compare triangles ADE and DEC using perpendicular EN, we see that their areas have the same height EN. That gives us the ratio of side A to D divided by side A equals the ratio of area of triangle BDE to the area of triangle DEC. Let's call this equation 3. Now, since the area of triangle BDE equals the area of triangle DEC, combining our results gives us A to D divided by D to B equals A divided by EC. This is exactly what the basic proportionality theorem states. So the proof is complete. By using area comparison, we have shown that whenever a line is drawn parallel to one side of a triangle, it divides the other two sides proportionally. Quick insight, this proof shows the power of geometry. Even something as abstract as proportionality can be proven elegantly with the concept of areas. And that, students, is the proof of the basic proportionality theorem. In the next lesson, we'll apply this theorem to solve advanced problems on similarity and scaling. Stay tuned. Hello, students. Let me begin with a little puzzle. Suppose you have a triangle and you draw a line that cuts across two sides. Now, if that line divides those two sides in exactly the same ratio, what can you say about the line? Could it be just random? Or does geometry force it to behave in a particular way? That's exactly what we explore in the converse of the basic proportionality theorem. The theorem says, if a line divides two sides of a triangle in the same ratio, then that line is parallel to the third side. Let's put this into math form. In triangle ABC, if side A to D divided by side D to B equals side A divided by side EC, then line D must be parallel to side B to C. Let's call this equation 4. Now let's see how the proof works. We use contradiction. Suppose line D is not parallel to side B to C. Then we can draw another line, say DE dash, parallel to B to C, meeting side A to C at a new point E dash. By the basic proportionality theorem itself, this new line would give us the ratio A to D divided by D to B equals A dash divided by E dash C. But wait, our assumption already gave us A to D divided by D to B equals A divided by EC. For both ratios to be true, point E must actually coincide with point E dash. That means line D and line D dash are the same line. Therefore, D must indeed be parallel to side B to C. So, the conclusion is clear. A line that divides two sides of a triangle proportionally cannot just float anywhere, it is forced to be parallel to the third side. Quick insight: ratio equality acts like a strict rule in geometry. It doesn't allow any freedom, it automatically forces parallelism. And that's the converse of the basic proportionality theorem. In the next lesson, we'll see how this powerful result is applied in solving real-world and exam problems. Stay tuned. Hello students. Let's work through a classic example where we apply the basic proportionality theorem in action. We are given a triangle ABC with line D drawn parallel to side B to C. Our goal is to prove that side A to D divided by side A to B equals side A divided by side A to C. Let's call this equation 5. Now let's begin with what we already know from the basic proportionality theorem. Since D is parallel to B to C, we can directly write side A to D divided by side D to B equals side A divided by side EC. This is equation 6. Next comes a clever step. We add 1 to both sides of the equation. So, A to D plus D to B divided by D to B equals A plus EC divided by EC. Simplifying this, we get side A to B divided by side D to B equals side A to C divided by side EC. Let's mark this as equation 7. Now, if we rearrange this proportion, we arrive exactly at what we wanted to prove. Side A to D divided by side A to B equals side A divided by side A to C. This is equation 8, and that completes the proof. So the sequence is simple. Start with the basic proportionality theorem, manipulate by adding 1 to both sides, and carefully rearrange to reach the required result. Quick insight: sometimes proving proportionality is less about inventing something new and more about skillfully reshaping known results. That's the power of algebraic manipulation in geometry. And that's how we prove proportionality inside triangles using the basic proportionality theorem. In the next example, we'll see how this connects directly to solving numerical geometry problems. Stay tuned. Next comes a clever step. We add 1 to both sides of the equation. So, A to D plus D to B divided by D to B equals A plus EC divided by EC. Simplifying this, we get side A to B divided by side D to B equals side A to C divided by side EC. Let's mark this as equation 7. Now, if we rearrange this proportion, we arrive exactly at what we wanted to prove. Side A to D divided by side A to B equals side A divided by side A to C. This is equation 8, and that completes the proof. So the sequence is simple. Start with the basic proportionality theorem, manipulate by adding 1 to both sides, and carefully rearrange to reach the required result. Quick insight: sometimes proving proportionality is less about inventing something new and more about skillfully reshaping known results. That's the power of algebraic manipulation in geometry. And that's how we prove proportionality inside triangles using the basic proportionality theorem. In the next example, we'll see how this connects directly to solving numerical geometry problems. Stay tuned. Hello everyone. Let's look at a very interesting application of proportionality inside a trapezium. We are given trapezium ABCD, where side A to B is parallel to side D to C. A line EF is drawn parallel to side A to B, intersecting side A to D at point E and side B to C at point F. Our goal is to prove that side A divided by side ED equals side BF divided by side FC. Let's call this equation 9. To begin, we join the diagonals A to C and let them intersect EF at point G. Now focus first on triangle ADC. Since EG is parallel to D to C, by the basic proportionality theorem we can write side A divided by side ED equals side AG divided by side GC. This is equation 10. Next, Look at triangle DCAB. Since CG is parallel to A to B, again by the basic proportionality theorem we can write side AG divided by side GC equals side CF divided by side FB. This gives us equation 11. Finally, by combining equations 10 and 11, we eliminate the common ratio and conclude that side A divided by side ED equals side BF divided by side FC. This is our required result, equation 12. So we've proved the trapezium proportionality theorem by carefully using the basic proportionality theorem into different triangles and linking them through point G. Quick insight, sometimes one cleverly chosen auxiliary line, like joining A to C here, is the bridge that unlocks the whole proof. And that's how trapezium proportionality is established. In the next example, we'll see how similar constructions help us solve even more complex geometry problems. Let's pause and summarize what we've discovered today. Two triangles are similar if their angles are equal and their sides are proportional. Thales observed that in equiangular triangles, side ratios are always equal. The basic proportionality theorem, a parallel line divides sides of a triangle proportionally. The converse, if a line divides two sides in the same ratio, it must be parallel to the third side. These theorems form the foundation for deeper criteria of similarity like A to A, SAS, and SSS, which we'll study next. So, triangles aren't just simple shapes. They carry the secret key to proportionality in geometry. And that, students, is the essence of the similarity of triangles. In the next video, we'll unlock the specific criteria of triangle similarity. Stay tuned.